Hello, this is Evgenii Kovrigin, NMR director at the University of Notre. Today, we will discuss a technique called reference deconvolution to improve one-dimensional NMR spectra, which were distorted due to imperfect shimming. The line shape improvement comes at a cost of reduced sensitivity, but may help if it is not possible to reacquire data with better shimming. NMR is relatively insensitive technique. We need relatively large samples to collect enough signal. It is important that all parts of our sample are experiencing the same magnetic field. This way, signals from every part of the sample occur at the same frequency and will add together to form a tall, intense resonance. However, if shimming is not perfect, the magnetic field will be different in different parts of the sample, and corresponding resonance frequencies will lead to peaks occurring at different positions. When added together, these signals create a non-symmetrical peak with a distorted shape. A very important consequence is that every peak in the spectrum will have this similarly distorted shape. If we have a strong singlet resonance in the distorted spectrum, we can use its shape to convert the distorted spectrum into a more perfect one. This procedure is called reference deconvolution. For the reference deconvolution to work, we need to have a strong, well-resolved singlet in the spectrum. In this spectrum, I have this peak, which is a singlet, and it seems to be reasonably symmetrical and have a nice line shape, except when we look closely, there are more components than one. If I quickly fit it, there are two resonances, which are composing this peak. These are signals coming from different parts of the NMR tube. So, how do we deal with this? First, we need to make sure that our spectrum is processed with appropriate parameters. I loaded my spectrum, I selected, and then check the apodization. It needs to be exponential, half a hertz is appropriate for now, and we can change it later. I will say OK. Now, zero filling. We have 65K points acquired. I will quadruple this size to make peaks more smooth. OK. Phases need to be adjusted. I hit auto phase correction, and then I'm going to check if phases are good for me. I need to see the baseline continuing from one side of the peak group to the other side, which is this is not. So I will do manual phase correction. I'm going to move a pivot to the group of the peaks on the left and zoom into this region. So I need baseline continuing, so I will adjust pH 0 and now zoom out, and we want to adjust pH 1. This will be OK, and now we will look at the peaks on the right and see if the phases are good. Yep, so we are ready to go. My final step is to correct the baseline. I'm gonna zoom full. There are distortions at the ends, and the baseline is generally curved. I will use multi-point baseline correction. I will put in 200 points for the RMS calculation span and begin adding manual points. Now I'm going to increase the intensity and zoom. I hit Z, zoom into this region, and pick points again. Actually, I can pick a point closer to the peaks. Shift left arrow, and now Z, zoom into this region, and it's pretty good here, but I can pick an extra point somewhere as well. All right, zoom full. We need to make sure that the points are sitting in the middle of the noise band. These points are a little too high. I'm gonna grab the point and move it until it is showing in the middle of the noise band. I accidentally added another point. Good enough. I'm gonna preview. The baseline is straight. I'm gonna say apply. And now we're gonna cut the parts of the spectrum which we don't need. Hit X, and then I can remove this part, and the noisy vicinity of the solvent signal. Hit Escape and save. Command S. The spectrum is ready. One word of caution. Reference deconvolution is very easy to apply and kind of difficult to undo in MNova. So usually I duplicate the dataset before I apply reference deconvolution and play with parameters. I will select the page, Command C, Command V, and it makes another page, and this will be my document I will be working with. To use reference deconvolution, I will need to find well-resolved, high-intensity singlet. This will be an example of the line shape, which software needs to correct for. So this will be my singlet resonance, and if I zoom closer, we see a distortion due to imperfect shimming. My next step is to go to Processing, More Processing, and select Reference Deconvolution. It automatically goes into the mode for selecting a region. I need to start from a baseline and then end with a baseline. The red line is proposed line shape, which will be put in place of this distorted peak. We are accepting parameters that the automatic algorithm chooses for us. We will use Lorentzian, and I'm not gonna cover the advanced options and satellites. You will read about it in a manual. So once I click OK, this distorted peak is turned into the perfect Lorentzian line shape. Now we can turn it on and off as we need through the processing template, more processing in this section, reference deconvolution. If I say apply, it will return back where it was. I'm going to go into full spectrum, and then I will go to this particular region where I have lots of different peaks, and for example, this is a particularly ugly overlap of multiplets, and let's see what reference deconvolution does for us. So, processing template, go to more processing, and I click and I hit apply, and this is now much nicer spectrum, which is easier to analyze. Once I say OK, entire spectrum is processed with reference deconvolution, so everywhere where you look, the peak shapes will be corrected. Here is an important note on when to use reference deconvolution. Our spectrum has some signal intensity and some specific noise amount. We use signal-to-noise ratio as a measure of sensitivity. The best option to improve the line shape is check it while on a spectrometer and improve shimming. If you succeed, your signal-to-noise ratio is increased because all the area of the distorted shape is now added to the area of the peak, making it taller. If you cannot improve shimming for whatever reason, or it is too late because you are looking at a previously acquired dataset, try reference deconvolution. An important caveat is that it makes your spectrum noisier, reduces signal-to-noise ratio. Therefore, if you have a lot of signal and very high signal-to-noise ratio, which you don't mind to trade for the peak shape, go for it. If your signal-to-noise ratio is low to begin with, using a reference deconvolution may increase noise enough that peak shapes become distorted by the noise. Try both ways and use your judgment.